Excellent. Welcome, everybody. How are we all today? Feel free to turn on your cameras. It's always great to see everybody's lovely faces. I see lots of people that I recognize. Um, Hi, I'm Nick Gross. Some of you may know me already. I am a proud freedomista, and we want to welcome you to this event from the Freedom Festival 2025. We're so glad you're all here, and we want to welcome back those who are have attended other events already and other parts of the festival. But for those who are here for the first time, uh, I am want to give you a little introduction to the Freedom Festival. The festival started in 2023 in response to a desire to create, through celebration, a conversation and play on what freedom means to our communities and to celebrate guaranteed emancipation and independence. In the U.S., that's goes from Juneteenth to July 4th, and so over a course of 16 days. The celebration is created by ordinary people, among them artists, scientists, creators, organizers, enthusiasts, giving and inviting others to explore freedom in all of its forms and meanings. We hope that you will take a moment to look at the Freedom Festival website, which somebody's going to put in the chat. If I'll put it in the chat in a minute, if nobody puts it in the chat, and to see um, what excellent roster of events that we have, both in person and virtual, like this one, and sign up for the Freedom Festival newsletter and also register for various events. Again, welcome, and we hope that you enjoy this session. Leading us today, and leading us and leading me today is Carolyn Selfon, a physicist and educator, and who was gracious enough to also reach out to me and ask me to join her in this exploration and guiding through this exploration of the quantum realm, a tiny piece of our understanding of the quantum realm, and so I'm gonna turn it over to Carolyn now to get us started and share a little bit about what she wants to do and what she wants us to do.
Yes, welcome everybody. So great to see you. If you can share a little bit about where you're joining us from and what brings you here, have you, played with quantum before? Are you brand new? Of course, this session is intended, we are welcoming people who have, not done any quantum before. Or who have. Um, and yes, and I'm joining from, well, I'll put it in the chat later, but hi, I am joining from Toronto, Canada. Toronto, Ontario is where I am physically located at the moment. And yeah, so I got into physics basically by asking why? Anyone curious here? Do we have any people who are curious who like asking questions? Yeah, so I was one of those like, but why children? We all understand where we're coming from, right? And and so asking, well, actually, yeah, since we're cultivating ensembles here, so asking why with people led me into theater, and asking why in the physical world led me into physics. And I just got really fascinated with quantum physics. I think I was kind of in middle school when I read a popular science book about it, and just how quantum physics really challenged the ideas that physicists previously held about how nature works, and that nature is actually, in some sense, even more creative than us sometimes, right? Although we get to be so creative in trying to understand nature. And so the way I describe, what I do, what physicists do, is we observe how the world works, right? We all observe things. We all, as humans, try to generate explanations, right? For, hey, maybe it works this way, maybe it works that way. And then we try to test those ideas, right? So we design experiments to test those ideas and to refine those ideas based on the test. And it's really fun when the results are surprising, right? And that's part of the story of quantum physics. Um, and yeah, and I do want to emphasize, and we all bring different models. And in science, basically, no model is completely correct. We can never prove it correct, but some models are very useful, and so we'll be playing with a couple models in particular today. And I would like to invite Nick to also introduce yourself as well a little bit further.
Sure.
And I am so glad that Nick has joined me. And we will also be having the amazing Simone Hyatter Adams joining us later on, which I'm also very excited about.
So I'm also a PhD physicist, and I remember I was always reading about atoms and small things and the edges of our understanding. And but the thing that got me really excited when I took a first sort of mid-level quantum course, and we used the mathematics that had been introduced to figure out how you could walk through walls. Maybe not you completely, but at least an atom could walk through a wall and 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 keep going. So and I'm reminded, I don't have the quote quite right, but there's a Shakespeare quote about nature is even stranger than your philosophies, Horatio. Right? So um, and so it was and so continuing to understand the strangeness of nature and how it works on all these different realms is an interesting challenge.
Yes. Excellent. And since we are all aided in exploring nature through building off of each other's ideas, we would like to invite you to get to know each other a little bit next. So, so I we will the amazing. Oh yeah, also shout out to amazing Stephen who is helping us run tech. So yay, Stephen. Um, and yes, give him lots of thanks, and we'll give him lots of thanks at the end as well. Um, and uh, and yeah, so Stephen will put you into breakout rooms, and I would invite you to briefly introduce yourself. It'll be too short, as these things usually are. Just share camera if you're comfortable, if you can, because it's always great to connect with people. You do better science that way, right? When you can see the people, and to just share a favorite question or a wondering that it could be that you bring to this question or that you had as a kid, as you like.
It's hard to watch for my cue from you and watch everybody
And
else at the
watch
same
everybody
time.
else. Yeah, yeah. Woo!
Wait,
Okay, how was that?
wave chaos.
Well, it's
Wave
kind of
chaos,
fun.
yes.
I actually realized I thought I thought "Huh, I'm a wave, but I'm dependent on the person ahead of me to be able to function.
Or you're part of a wave. Yeah, yeah, exactly. Awesome. I love that, Martha. Thank
I
you.
think we got to put a pin in that to come back to it later, right?
Yeah,
I
I mean, we can also
Yeah.
play with it now. Yeah, go ahead.
I also wondered about being able to see different waves at different times. Like that like Anne had started something and then
Mhm.
that it wasn't before me, like people didn't pick it up, but I saw Anne and then I was like, well, who said that I'm seeing the wave in a straight line? Maybe it's actually curving, or like how would I know where or when I'm seeing a wave? Um
Mhm. Neat.
Might there be some bodies that would refuse to do a wave in
Ooh, interesting.
in space?
there's there's sort of there's like a like a when the ropes, like two different size ropes are connected and you get or an impedance. That's the word I'm looking for.
Oh, it's a classic physics problem for sure.
Could for someone who's an ignoramus about this, like I am, could you tell us why we're doing waves? I know we do that at the baseball games, but I'm not sure why we're doing it.
We will build on that. So what, yeah, so the next question is, what is your concept or mental model of a wave? And then yes, we will tie it into a to the models that we have found to be useful.
Are you asking?
So raise your hand, share in chat. Yeah.
Can I ask a question about the
Rochelle.
question?
What is my concept of a wave? I experience it meaning something about moving energy
Cool.
around.
Awesome. Thank you. Yeah, and Gwen, you had a question about the question?
Well, I think Rochelle Ann helped me because I didn't have a concept of a wave. But the thing that did come to mind, that's what I was going to ask. What if we don't have a concept of it? But the thing that did come to mind was what you would associate as a wave with water.
Mm.
And so I could see it then. I do have a concept, but I don't know where it starts. Do you know where the wave starts?
But certainly, so picturing that
Well,
ocean on a beach and the waves going, right? Yeah. Would anyone else like to share your concept of a wave? And yes, physicists are welcome to share too.
Well, I grew up with radio waves.
Mhm.
So I have this concept of there's these waves in the air that I don't see that the radio can
Yeah.
pick up.
Yes. Super cool.
Well, I'm reading Carlo Rovelli, and I have to reread it like 15 times to get one concept, but I'm going through it very slow. And waves have something to do with matter and light, I think.
Sure. Sure. And I would say everything has to do with matter and light. And yes, including waves. Yes, absolutely. Absolutely. Yeah, thank you.
Did we
Thank
talk about the wave hello, which is kind of funny because as I'm thinking of a wave hello, I'm like, really? Is it a wave? I'm like, I don't know.
It's another way of yeah, maybe it starts a wave somehow, but yes, so in the models that I tend to use, that physicists often tend to use, a wave, I think Rochelle captured it very well in terms of there's something that's propagating, but it's a pattern rather than an actual thing. Right. So like when we were doing the wave and sending it down to, it was Stephen at the end then, like my hand stayed here, right? My hands but the motion I did with my hands propagated across the screen. No, Carla didn't see it.
Carla,
Carly.
here, unmuted. We didn't see any wave.
You didn't see the wave? How about do you see people across the top or no? Or maybe go to
No.
gallery view? Ah, go to gallery view.
Okay.
That is a good point.
I don't know, this with the new version of Zoom that I've got, there's no gallery view. There is participants.
Maybe Stephen, would you be able to chat with Carla to see if you can get her to gallery view?
Yeah, absolutely.
Awesome. Thank you so much, Stephen. But you can also, Carla, you can also imagine like a wave in a stadium, right? Where like the motion translates across, but the effect moves, but the actual people stay in one place. But the effect might move all across the stadium versus me like doing this and running all across the stadium.
That's actually very interesting because what I was going to ask is whether particular particles have to continue and actually travel the whole way of a wave.
Yeah. And yeah, what we
And
just
in
saw
this
with
case, they
our wave
don't.
is, and yeah, exactly. In this case,
Okay.
we don't. And yeah, we
push the air.
Well, we
exactly.
push the air, yes, but
And circulation in your body.
yeah.
Yeah, and when you push the air, what kind of wave do you think of with that, Alfred?
No, well, I mean, you force the air to move in all sorts of directions.
I've got gallery view now, except everybody is separate.
Okay.
Yeah.
Mhm.
Well, that's the idea.
But
Yeah.
how would one do a wave then?
Oh.
Should we do it one more time for Carla?
Yeah.
We'll show you.
Okay.
Yes.
Okay, let's do it one more time. You see it, Carla?
Yeah.
Oh, we
Go,
lost.
Rachel.
We lost
Rachel.
Raquel.
And there, Alfred, you going to do it too?
That's okay. Fun is enough.
Well,
Okay, we got the idea. Awesome, thank you. Okay. And so yeah, so things that came up from that conversation included light, right? I think Anne mentioned light, Dan mentioned radio waves, Gwen mentioned water waves, and Nick will introduce us to another kind of wave. And again, waves are one kind of useful model.
Right. So I don't. If you've got it handy, I don't want anybody. We're short on time, or we're trying to stay on a schedule. But if you've got it handy and brought an instrument, oh, it won't because I'm on a background. It won't. There we go. It won't fade in. So I have an instrument here, right? And, I can create sound waves. And now let's see if I gotta do this the right way. So um, I don't know if can you hear that? Oh yeah, you
Yes.
can. Okay, I got
Yeah.
my setting. I got my
Nice.
settings right. Yeah. So right, and so now actually I can create. So those are two different pitches with two different frequencies. So they've got two different notes, but I can also play them at the same time, right? So and that wasn't the there, that's a little more harmonious. And so the question is, one of the questions I think we want to explore is how to interact. And going back to somebody raised the question about sound waves and whether the sound is of course traveling. If we were in the same room, the sound is traveling, the energy of the wave is traveling, but the air doesn't have to travel necessarily. You're not just because somebody's talking at you, especially across a room, doesn't mean the air that they're yeah. If we did that anytime we were with Raquel, it would be like a she's talking all the time. um so I guess I wanted to talk, wanted to just invoke the idea that sound can blend together, these waves can blend together, and one of the things I think we want to explore is how those things blend together. Should we move on to the simulation? Because I think there's some things in there that are useful.
Sure. So we're going to show you a simulation of this of our model of waves here.
Right. And I'm going to put this link in chat because you can play with it. Oh.
Well, yeah. Well, you will play. We will give them a couple minutes. Oh, right. Yes, we want to let. Yes. So
I'm sharing this link in chat, and then you're going to open it up.
Right.
Yep.
Right. So if you can open it up, please do. And we'll bring you back in 2 minutes. So don't worry if you can't see us. If you are joining from a device where you cannot open that up, then we will then I will play with it here. And the main thing is see what patterns you notice creating waves in this way.
And there's all sorts of settings you can play with, but you can leave those alone and just play with the little wrench there that's holding the bead down and see what you notice.
So you grab the wrench and move it.
Yep.
Mm-hmm. Yep. But you can also play with the settings too if you like.
I don't hear anything.
No, there's no sound. We're just observing the thing.
Oh, wow. This is cool.
Yeah.
Yeah.
Trying to get
So
double
so it doesn't work. So you have to click on the link in the chat, right? You can't
Yeah, I didn't
interact
realize
with
that
it on
first.
the
Yeah.
with the screen share. I'm just playing with it for people if you can't act if you're like joining from a phone and you can't actually like, you know, access the simulation for right now.
It reminds me of doing a rope.
Yeah,
flip
exactly.
rope.
No, that's exactly what it is. It's just a, yeah, it's a rope.
It's very cool. Yours goes out a window, so it keeps going, and mine hits a clamp.
Make all different
Moves
kinds of
back out.
Yeah, and that
Yeah.
setting is you can do fixed end or no end.
Oh, that's what that is. Awesome. Okay.
So you get a choice.
No end. Let me try no end. Oh,
You can't move the wrench closer, right?
Nope.
Nope,
You can
just
only
up
move
and
it up
down.
and down.
Up and down.
oh, I like no end.
Yeah.
I was when we were doing the wave, I was reminded of that when when the wave got to Steven and it just fell off the end, right? So, so
Well, this wave looks like what you see in football stadiums when the whole crowd does this wave that looks like moving through. Each person is like fluid with the next. So the wave is just going up and down. If you know what I mean, it looks like
yep.
Yeah.
people are making a rope wave in the stadium. Looks just like this.
I just switched to slow motion and it looks like there's
Cool.
the beads or whatever, the particles are spacing out in the beginning, but then they're getting crunched up at the end. I don't know how to describe that.
I just tried
Yeah.
that. Yeah.
Oh, wow. Ah. Oh, God.
So that when they hit the other, I don't, is it a vise? From the
Mhm.
wrench to the,
Yeah, you can
when-
call it that. Yeah.
so the little green ball is in the vise
Yep.
and then it stops and it has to go back the other way.
Mm-hmm.
Unless you move the wrench
end.
up and down. It's real interesting.
No, that I've done.
With the slow motion,
Yeah.
it's really amazing.
It seems kind of fixed at the end there, right? With the green ball and the
Yeah.
vise.
Going out the window, though,
Do the
somewhere.
green balls have a different property?
Good question.
Great, really great question. They don't. It just makes it easier for you to see.
Uh-huh.
Right. So so yeah, I think most of you are saying it that like it's not, there's nothing, each little bead is each little bead is only moving in what direction do you see the beads moving in?
Left to
Right.
right.
Yeah.
The beads themselves. So look at like watch
Yeah.
the green bead.
Oh,
Does the
they're just
green
going up
bead
and
move left
down.
or right?
the
Right.
green, oh,
Left to right.
Oh, yeah. Good point.
And so the green bead makes that clearer to see that
Yeah.
the beads are just moving up and down,
Right.
but the pattern is moving left to right. Here, it's probably easier if I do it with no end. So we have this pattern, whatever pattern of motion I make moves left to right, while each bead itself only moves up and down.
So
And we can relate this as well as Rochelle already did, right? Rochelle already pointed out for us that this is kind of like a wave at a football stadium, right? Like you don't have people running from one end of the football stadium to the other. So if each person is a bead, you know, they move up and down, but then that wave can travel the whole stadium.
Yeah.
so
You move the wrench up and down fast, but then you stop. You see it.
Mm-hmm.
Like the wave continues a little bit after you, and it even comes
Yeah.
back. It's
Yeah. This must have to do with power, influence, connection, building. I have to add Christmas.
Yeah, Nick, did you want to make additional points on this? Do you have other things to add, Nick?
I don't know. I think we've covered
I
most of
think
it.
we've done this for, have we finished the 2 minutes of play? Because I haven't been timing it.
We probably
Yes.
did.
Yes, so I
Okay.
think we finished the 2 minutes of play.
I'm
Yes.
sure
Okay.
And we've had plenty of discussion. I was trying to grab some notes, just to see what people
Awesome.
people observed. I made some notes here.
So I wanted to build with any other questions or observations. I thought those were great questions and observations. So this idea of waves. So again, in our model of waves, it's a pattern that moves, but the things making the pattern just move up and down. They don't move in the direction of the pattern. So the pattern is moving in a different direction than the things making or the pattern is moving a much longer distance, I should say, than the things making the pattern.
I had an observation that
Yes.
occasionally it would look like there was a jump rope at the end because I was trying to get that jump rope effect. And I
Yeah.
love the simulation. Like they did a beautiful job. It's rare that I ever see a simulation so fluid. Right?
Yeah.
That was gorgeous. And then my other one was like, what's this got to do with quantum?
Cool. We
Really?
will get to this. We are building to this. Excellent question. Keep that, hold that. So now we want to look at how waves combine. Okay. And so Nick's going to share a video and we just want to observe and describe what happens in the video.
Okay.
So now we're going to have 2 waves in this video and we're going to see what happens to those 2 waves.
We have to get out of this page.
Oh, are you not back to the, sorry,
No.
I guess we didn't properly welcome you back.
How do I get back?
Welcome back. Come back to Zoom.
Come back to Zoom.
Just click on Zoom.
Yes.
Yep.
Okay.
just close your.
But yes, thank you for going out of Zoom to play with the simulation.
And you should see my this video.
Yes.
Okay. So can someone describe what happened? What did you see?
It was a wave. I saw a wave go across.
The last one was like a slinky. Like,
Yeah, it's a
It looked
slinky.
like
Yeah.
some kind of animal doing the wave.
Nice.
Should I pause it?
Oh, maybe it's a human doing the wave.
Yeah, it's humans. It's humans on the edges.
it started
the thing
from
is, what
both
do you see?
ends and then sort of stopped in the middle. Okay, or when they met, seemed like.
Yeah, Nick
What?
paused it.
I paused it. Yeah.
Oh,
So you could
And
see.
there-
Yes. What
Ah,
observe?
okay.
What do you see happening in the middle, and what do you see happening after the middle?
In the middle.
To a
Keeps
Could-
show, and then it goes. We'll
Can
see.
you show it again?
Oh yeah. Oh yeah. It goes up and down, up and back. It's high in the middle and back down.
Well,
we
it
have
also
any-
is going in the opposite direction. And it's
Oh yeah.
Cool. So one possibility of what's going on here is they're bouncing off each other at the middle.
Yeah.
That's one possible explanation. So we're making an observation. We're saying like, oh, one possible thing is that they bounce off. The 2 little waves bounce off each other. Any other possible explanations? Any other ideas?
Because it's going into the middle and it can't go any further, so it turns.
So yeah, so
But
it's they
why?
come together and they bounce off each other.
Yeah.
I mean, it could be that the other human is just flicking her hand, and
Okay,
that sends
cool.
it back.
or they
So
keep.
just for
go-
time.
Yeah,
Oh,
sorry.
yeah, go ahead. Sorry, Lisa. Yeah.
Well, I was going to say they keep, each wave keeps going, but they sort of, for some reason, when I don't know, it seems like they lessen when they meet. Like the I don't know.
Well, there is yeah. It's along a floor, but yeah. So Lisa, what I'm hearing you suggest is that the waves keep going, so they just kind of go through each other when they meet at the middle.
Yeah, it looks like they're bouncing off each other, but it could also be that they're just
Cool. So we have 2 possible ideas. So let's think about how we might test which idea works. Would you enjoy going into breakout rooms to test which idea works?
Sure.
But couldn't we talk a
Okay.
little bit about Before we do that, how do we
Yep.
test? What do we?
Yeah.
What,
That's what I was
what does
No,
it
we're
mean
gonna
to test?
talk about it first. I'm just gonna give you the slide deck for breakout rooms where you'll put your ideas. Okay, but Nick's gonna also screen share, show you the slide deck, show you how to draw on the slide deck and all of that. So we'll make sure that everything is clear before we put you in breakout rooms.
So here's the slides, and you should be able to.
Can you make the first one bigger just so we can see it? Okay.
This one?
Yes. So is someone able to share what experiment you see in that image?
The Slinky experiment,
Mm-hmm. Is it the same one we just saw, or is there a difference?
same one.
I can't tell.
Not
It's
moving.
not.
No,
It's
They
not
start
moving.
at different points. They start upper and lower, it looks like whereas last time I think they started at the same place.
Can you maybe go to slideshow just for the slide deck
Sure.
so we can see the whole thing? So we can
I don't
see
know
it
if I'm
clearly?
right. I'm just, is that?
It looks like
Oh
the
no, I guess
person
that
on the
won't work
left
for
is
this.
going
Okay.
side to side rather than up and down.
So just to be clear, here's the Slinky.
There you go. Yeah, that helps too, Nick.
I
Okay,
don't
so
see.
in the previous experiment, both ones were like little mountains,
Up and
if you
down.
will. I don't know if you can still see my video. Whereas in this one is a valley and the other is a mountain.
Yeah,
But it's again, we have little waves being generated at each end, and they're going to meet in the middle. And we have two possible ideas that when they meet in the middle, either they bounce off of each other, or they add together and or they pass through each other.
I don't
Okay.
see the person on the right. There's a person there.
There, yeah, you don't worry about it. But yes, there are
Okay.
people on both sides. And so does anyone have any questions about the experiment?
Does the light have any importance?
No, it's just reflections.
Okay.
Yeah, so there's a hand here and there's a hand here.
Mm-hmm.
Right.
I don't know. It looks to me like unless the person on the left is starting up high, it looks like they're going to the side rather than, you said it's a valley.
Yes. Yes. Nick, can you circle that in purple or something? Or whatever
Sure.
color
So
you
this
want.
is yeah, I mean they're sitting on the floor,
Right.
right? And this one
That's the
started.
valley.
That's the valley.
Right.
Going,
Going
and
then and the valley's moving to the right and the hill's moving to the left.
Mm-hmm.
I'm confused, but that's okay.
Lisa, they're both going sideways, I think.
I wonder if as
Looks like
long
Well, are they though? That's what I was saying, that it looked like that, but
Let me also put our original video in the chat in case folks want to revisit that too.
yeah.
But
And
my question is, what is the experiment here?
We have the two waves, one a valley, one a hill, going towards each other, and you're going to make predictions based on the two, based on one or the other explanation, based on your breakout room.
So I think we're thinking it's a thought experiment, like thinking it through.
Well, we're going to actually show you. We're going to actually do it after, but first we're going to make predictions
In a breakout room.
Yeah.
Yes. And Nick, can you show them where they're going to record their ideas?
maybe. I mean,
Maybe I should. I mean, I can also screen share if that's easier.
So they might. Do you want them to try and draw in the shared
Yes.
document?
Yes.
Okay. So we want to put
I
that
already
in
posted
chat,
it in the chat. That
so
I've
you
got.
should be able to open that up.
I can post it again if you all.
You should be able to open that up.
Is it
And when
the Google Doc.
It'll be a Google slideshow. And so
right in the got it.
You should be able to then grab a curvy line here on this toolbar and draw what you think, some like, oh, that's not the line I wanted. Scribble. I want to scribble.
So we're showing you how you can draw on it. You can also
so
just
I can grab a scribble here
Where?
on this toolbar up top. Once you've got the Google Doc open, on this toolbar up top.
Maybe we could go to the breakout room and call for help if we need help drawing.
let's do it.
That
Let's
sounds like
do
a
it.
great
Okay.
idea.
And so there's, and the thing is, Nick can show that there's one for each group. So there's group 1, group 2, group 3, group 4. So just go to your group slide. Okay,
Great.
let's launch the breakout rooms.
We'll figure it out together. Yes, we will.
Yes.
Or we won't.
Or we won't.
So does someone from group 1 or 3 want to share our prediction if they bounce off of each other, what it would look like? And I can also try to draw it on here too. Try to draw what I hear, and you let me know if if it makes sense.
If they bounce off each other, then they would return to their previous location.
Oops, no.
In the same direction.
Yeah. Okay, Martha's kind of doing it. Yeah. So if they bounce off, then we'll end up with one down here going this way, and one up here going this way. If they bounce off.
But in the same.
Oops.
Okay,
you cleared it for me. Great, thanks.
I'm sorry.
No, that I was trying to clear it. Group 2, do you want to share what would happen if the waves pass through each other?
We had
or what was your prediction?
2 ideas.
Mm-hmm.
Awesome. 2 predictions. One was that they'd cancel each other out, so you'd get a straight line.
Okay, cool. So a straight line here.
Yeah. And then the other was that they would be flipped. So
then you get the top, so you get the
hill on the
down
left.
one here and the up one here.
Yeah.
Yeah.
Cool. Okay, let's watch the video and see what happens.
Okay, that would mean I'd have to find the video.
That's a quantum challenge.
Okay. Oh, and this one. There we go. All right, so here we go.
Oh, I saw up on the left. Here we go one more time.
But then it was straightened out at the end, right?
Reverse.
I think if the flipped positions wins.
But it ended
So they
up
pass
as-
through. They pass through rather than.
Yeah, and then straight line.
It's true. But
no, we're both
And
right.
right at the middle, I think the other prediction also works out. Right at the middle, they cancel out.
So everybody's right.
So group 1's prediction again was.
It was for a different model. It was if they bounce off of each other.
Oh, okay.
And they would reflect off. Group 1 and group 3 were asked to make predictions based on that model.
As a proud member of Group 1, I have to say that we came up with the other predictions as well. So it wasn't our only prediction. So
Congratulations.
okay,
that is awesome.
Just say so.
No. I mean that is the correct prediction for that. If that idea
model,
were right, and that's part of the point is that we enjoy testing ideas whether they're right or wrong, right? And so it's very exciting to be like, oh, we tested this idea and it was wrong, and this other idea. If we only have one idea, then we can't really distinguish between ideas, right? And so our test allows us to distinguish between these two possible ideas.
How and who determine who's right?
What?
How and who determines who or what's right?
So in my model, in my understanding, like there is no single right answer, right?
That's what I was thinking.
But we can get closer and closer to more and more correct answers, right? So we could rule out the model that they bounced off of each other. We couldn't tell from the first one. That was a perfectly great idea, right? Maybe they bounce off of each other. But then we did that experiment, and that experiment is not consistent with the idea that they bounce off of each other. The second experiment. right? So we can say, oh, it seems like they're not bouncing off of each other. It seems like they're passing through each other. Cool. So now we can build on the idea that waves pass through each other and that they can cancel each other out, right? Because if they bounce off of each other, they never cancel out. So shall we see some cool things about what happens when when things cancel out? And we'll try to do this quickly.
Sure.
I'm going to go back to.
So far we've been working in one dimension, right? Like a wave on a string. So a violin string is a 1D wave, right? So, and it gets it's the same physics, but it gets a lot more fun in multiple dimensions.
Okay, so here we have just water waves. So this is a device here that's pushing water back and forth, creating water waves. And then there are two slits in this here that will be like two sources of waves. And this is just showing you. So we're seeing waves and we're seeing places where they cancel out here and places. This is just showing you the simulation that I'm going to show you next. Okay, so those are the two sources there. And then to really see what happens, we're actually going to go to a simulation here. Nick will put the link in the chat, but I don't think we'll have a lot of time to really play with it for everybody to play with it. But you may want to play with it yourselves after. So if you want to play with it, it's waves interference, and this is the water waves. So I'm curious what people are seeing. And this should connect to what you're seeing here.
I want an art history degree so I can describe what I'm seeing.
Well, each drop turns
Nice.
into a wave, doesn't it? Each drop looks like it becomes a wave.
Mm-hmm.
Because the colors get bigger.
It goes from a dot to a string.
But what in this case, actually is moving?
I was going to say they're moving.
So the water is just moving up and down. Right? But the pattern is spreading out. And so where the water is up, that's the light blue. Where the water is down, that's the dark. So again, we can go back and forth.
So funny, because I definitely think of waves in water as water moving.
Mm-hmm.
I always think of it as like where
waves on a beach. It's true. They do carry water as well.
So waves that break on a beach are different. They sort of operate under some different physics than waves that are traveling in the deep water.
Yes.
So what?
And so this is just if you were like in a bathtub or a pool or something, and you just did this with your finger.
Okay.
Or if you drop a pebble in water.
In a lake.
In a lake. Yeah, and I don't have that video with me, but I do have one of those videos too that can show you that. So the testing experiment for that, which is a great idea, Raquel, is you put something floating on the water and then you throw a rock in. Right. So if you have like little leaves or something that you can float in the water, or like a beach ball or something that you can then retrieve, and then you put in a stone, drop in a stone or something and watch the ripples, the beach ball just goes up and down. It doesn't actually go out with the wave.
And different colored water would be also, right? Like if you had water.
Yes, that's true. Yeah, exactly. Yeah, absolutely. That would be another great testing experiment. Yeah, so if you had water that was like blue over here and had green over here or something, you could also check it that way. Yeah, exactly. The water is moving up and down. And then here, this gray area, these gray lines, this is where the waves cancel out. And so we can have waves cancel out, and we can have this for anything that behaves like a wave. So we can have this for, or anything that our wave model works for. So here we have it, again, a simulation, but it's sound. And here we have stuff canceling out, and here we have stuff canceling out. and you know, we have noise canceling headphones, right? We have various ways of that we might want to cancel out sound waves. And then lastly, we are playing with light waves here. And so we have these doing the same thing as the water waves, basically following the same model. And then I'm going to throw up a screen here. What do you think we're seeing on the screen? What does it look like?
Patterns.
Yeah, we're seeing a cool pattern.
They continue to cancel out. So
yeah, along these gray lines here, there's canceling out. Continue, Raquel.
But so the frequency, like the drops are faster. So I don't know. We're seeing more, like there's 1, 2, 3, 4 lines in the same area instead of the 2. And I don't know.
Yeah, that's just an artifact of I mean, we can change these by, you know, by moving these around. So there's different settings you can make that would change those. Yes, absolutely.
Carolyn, what does canceling out mean?
Zero level. The water level is neutral. So just like we saw with the two slinkies in the last experiment, with the two waves in the single slinky, we saw in the middle the two waves canceled out, right? One was up, one was down. In the middle, it just stayed neutral.
So where is this canceling?
Along here.
Oh, the gray
here,
lines.
the gray.
Oh.
The gray is the cancellation. And so then when we put a screen here, this black, that's where the waves completely cancel out. The black here, there's no wave there. It's completely canceled out. Whereas when you get big highs and big lows, like here, this is where you get the bright spot. There's a lot of energy here, right?
When they first start dispersing from the circles, it looks like we get squares for a minute. Rectangles, is that right?
Yep.
So we get different shapes and pattern because of the patterns.
I mean, basically, it's circles going out, and then as the circles combine, as the circles add, yeah, you get the different patterns. But it's just the two circles adding.
I see.
And yeah, we can move them further apart, you know, kind of thing.
And maybe increase the wavelength.
Oh wow.
Oh, no, that's good enough. That's good. Sorry, I meant decrease the wavelength.
Oh, okay.
Increase the frequency. So, but I wanted to see like the 5, like so you can get higher numbers of interference patterns.
But what we're getting this is, again, the waves are just going out. So again, I can stop one of them so you can see what just one looks like. Right. Actually move the separation back. Right. So you can see just one going out. They're just going out in circles. And this would be the same as if you dropped a pebble in water, or same model. And that's what's part of cool, is that we have this model of a wave, and then we use this model to describe various things. And of course it's not perfect, but it's, and then, so we just have one going out, and we can stop that, and we can have this one. So this one is also just putting circles out. And then we can do them together. And then we get this wacky pattern where we get these bright spots and dark spots.
Can you make each of them a different color?
What? Yep. Yep. And Nick has put this. I don't have my chat open, but I'm assuming, yeah, this is in the chat, so you can.
Is it the same fit?
It's the same company. It's a different simulation. Yes, gotcha. It's the same awesome group.
Remember when they started?
So
what does this have to do with quantum?
Yeah, great question. Let me turn it back over to Nick.
Well, Simone has joined us, and so I wanted to acknowledge that. Hi, Simone, Dr. Hader Adams. So, I'm wondering if we should just jump to the electron experiment.
We need to, I would talk about the mental models
Okay, great.
quickly. Yeah.
All right, great. Um, so one of the questions that we have, so you've we haven't talked about quantum, we haven't talked about atoms, we haven't talked about and the thing that we want to make a connection to is electrons, right? So electrons are part of an atom. What I'd like you to do, and we're gonna do this in the here it is. We're going to do this on the whiteboard. So I'm going to throw up a whiteboard, and what I'd like you to think about is what if I say to you, what is draw me a picture of an atom, or what is an atom, right? What gets invoked in your mind? And also, if I say to you, so a piece of an atom is an electron, it's a charged particle. Like, what is what does that evoke in your mind, right? And so, what do you think about? And I've got my mental model of that, but I want to see what your mental models are, and we can. Oh, thank you for sharing the whiteboard. So on the left-hand side, you can see there's some drawing tools, so you can go grab a pen over here. I don't, and so people I see people so there's a a blue pen on the top of that board is highlighted, and you can draw something. And so my question to you is, can you first draw me an atom or draw me an electron?
Nice. So I'm seeing orbitals, or seeing orbits, I'm seeing circles, I'm seeing dots.
How come I don't see my name?
I
You're
see your
there. I
name.
see you. Oh, you don't see your own name.
You don't
No,
see
You
your
only
own
see other
name yet.
people's. But I see your name. I see you're there, Rochelle.
so I can't even see what I'm doing.
Do you have the little pencil that you should be
I
able to see?
tried to. I
Oh,
don't know
okay.
if I went far enough.
Oh, nice. I'm seeing some zigzags and
Where am I?
waves.
Oh,
It
sorry,
doesn't. What?
well, you sound very frustrated. I'm sorry that you're.
You could come near me, Rochelle.
But when I go there, I don't see the pen going with me.
Oh, wait, I'll come to you.
You see
Where'd you
me?
go? I do. I did. My pin's right next to your pin. So you want to follow me? Where'd you go?
Jesus. I
That's fine.
lost you.
I did too.
You can also describe verbally or in the chat what your model is.
Sure.
But
I want.
Nick, I think we should is this good? Shall I close this?
I think this is yes, this is good given the time that we have. So
Awesome.
I'm seeing lots of squiggly lines. Actually, can you open it back up? Because I'll draw my mental model of an electron. Well, so my model for an electron, like if somebody says an electron, if I could draw a billiard ball with the lighting, right? It's got a oops, and I kind of missed, but it's got an E in it, right? A little billiard ball and a minus sign because I know it's negatively charged. So I'll try drawing it again. I got my billiard ball and my E and a minus sign. So that's what so somebody says an electron. Um, that's what I see. Carolyn was very so the orbitals, as Carolyn was saying, the electrons orbiting the atom, or maybe the little number of electrons orbiting an atom, or a big. There's the planetary model of the atom with the electrons orbiting the nucleus. And so and there's a few others I like this one. I'm curious about what it means, but I don't want to delve into that right now because I want to.
Can I switch to the next slide, Nick?
Oh, sure, yeah.
You can keep talking.
Yeah. Okay. Great. Well, I am forget what we're doing, or I know what we're doing, but or you're going to the yeah, right. Okay. So here's what we where this gets to the point. So the idea of quantum mechanics is that you're talking about stuff that's really small. And the question is whether the physics that we walk around here, the physics of billiard balls, if my model of my electron is a billiard ball, does the physics of a billiard ball really work? Right? At these really small realms. So somebody decided, well, let's do an experiment where we now fire electrons at two slits, much like the water experiments that Carolyn showed, and see what appears on the screen on the far side of those two slits. So I'm going to fire a bunch of electrons at this mask with these two slits in it, and see what appears over here. All right. Do we want to go through the prediction process? There's a couple of possibilities that we could have. Somebody think of,
What are we predicting?
What pattern will you see on the screen when I fire the electrons through these two slits? So I'm just going to have a beam of electrons. They're going to be coming out, more or less continuously, lots of electrons at these two slits.
Two straight lines.
Two straight lines. Okay. So if they just hit those and they just kept going, like the billiard balls, you get two straight lines. Any other thoughts on what you might see?
Can you draw it, Nick? Can somebody annotate it, or do you need me to annotate it?
Yeah, sure, I'll draw it. So,
my other guess was like the bands and the patterns that you showed us before.
okay. So it could be either two straight lines, or it could be the bands, right? So if it was the bands, somebody other than Raquel, what would that mean about the nature of the electrons? We saw the bands because we were doing light and water waves.
Well, just judging from your hint, they're waves.
Oh, right.
If we see the bands.
Right. If we see the bands, they're waves.
Versus if we see two splotches.
Two splotches, yeah. So okay, so that's I think that's good enough. I think we should go to the let's go to the
splotches. If they were splotches, what would they be?
I would say they would be particles, right? Because they're going straight on through the slits.
Gotcha.
Okay.
Thank you.
So the experiment that we're going to run is we are going to fire an electron beam electrons at these two slits, but we're going to do them one electron at a time. So if we play that video, just watch it. So just one electron at a time. Once you pause it right there, what do people see? So this is now looking at the screen that's on the far side of that double slit.
These are the electrons on the other side? That's what you're saying?
These are the electrons hitting the screen. Yeah, so the screen gets energized and it gives off a little bit of light, so you're able to see what the electrons when it hits them. They're high enough energy that it's like the old time phosphorus TVs, right? The phosphorus screen gives off a little bit of light when it gets hit by an electron.
So I see 6 dots, 7 dots.
Yeah.
8.
So individual dots, indicating like these are individual particles of electrons. And now it's sped up some, so we got more electrons, but they're all still coming through one at a time. What do people see?
Other than Raquel.
I see stars in the solar system.
Okay.
Nice. So we talked about two possible predictions: two big splotches, or a vague splotch, or bands, multiple bands.
Are these splotches we're looking at now?
Well, what do you see? What do you see?
Splotches that look like they could become something solid if they keep populating.
So is it just the two splotches?
4 spots.
Yeah, I see 5.
There's 5.
Yeah. 1, 2,
The
3.
bright areas.
Right.
Oh, the gray areas. Oh yeah.
Yeah. Can you run it? Can you run it one more time, Carolyn?
That's 5. I saw.
Yeah. Nope. Just okay. Yeah. You're gonna run it double speed. Okay. Excellent.
But is it still a cancellation?
That's what's wild, isn't it? How can single electrons cancel each other out?
Wait, you lost me there. Where's the cancellation?
Yeah.
Because there's the high spot, which is like the gray white, and then the dark bands. And the
These are
dark
the dark
bands,
bands.
when we were looking at the waves in water, meant that the waves were canceling each other out. Right? Where it was dark was where it canceled each other out, where it became, we didn't see the wave, we didn't see things moving. And so now when we're looking at these particles on the wall, we see the brightness where they're landing, but then we also see these gaps where what looks like a gap, that dark spot. So the language, if it continued, would be that area canceled out. But then what does that mean if they're particles going through
Exactly
a thing?
What does it mean?
And so just to try to sum up, right? So Raquel, you're talking about this canceling out here, right?
Yes.
Which we saw in the simulation, which refers to this dark spot here, bright spot, dark spot. So this is the screen, right? Again, this is a simulation, so it's a little bit more ideal. And we can see this in this video here. This is 2 slits, right? So this is 2 slits with waves, right? So it makes sense for waves to cancel each other out. These are the lines where they completely cancel each other out. And I can go back a little bit and just play this again. So you see how, you know, like they're producing waves, and then the waves just cancel out along these lines here. And then what we're seeing here, now we're just looking at the screen. So again, in this, we're just looking at the screen at the end here, which again corresponds to the screen here, but now we're looking at it head on. And what we're seeing is these bright bands and these dark bands, bright bands, dark bands. Yeah.
So
and that's, yeah, go ahead, Nick.
So what blew people away historically was, first, they were watching these individual electrons hit the screen, and you say, oh, there's a particle there because I can see it's hitting the screen, it's hitting it there, right? It's a ball, it hits the screen, it hits it right there, it deposits some energy. But then you start doing this kind of an experiment and you say, oh wait, it's got these wave properties too. So this is what historically was referred to as wave particle duality. You have both the electrons have both particle properties and wave properties. They're some like mind-bogglingly combination of both. And that's where it gets weird.
Nice.
And also awesome.
And also awesome.
Does that help combine, get it into quantum physics, make the connection for those who are like, what does this have to do with quantum physics?
No, because they still have to know what quantum physics is.
Well, I mean, basically, you just learned a bit of it. You just explained a bit of it, Raquel. And it's I mean, it's a whole bunch of models, right? And so if you want to learn more, we're going to explore more this fall. So we'll put that in later. But basically, it's this idea of electrons being quanta. And the thing is, light can also be particles as well, right? We saw light waves combining, but the light can also be. So it's this wackiness where small particles, for example, can be particles but also behave like waves, which doesn't make sense because it's hard to think of billiard balls would never do this, would never cancel out. You can't take two billiard balls and have them cancel out.
So let me try, because I'm not trying to be difficult, honestly.
Yeah.
It's that the idea of quanta is that a particle is both a particle and a wave, or has particle properties and wave properties.
Right.
That is a key part of our understanding of the subatomic world, the atomic and subatomic world that is included in quantum physics.
Got it.
Yeah, no, thank you. That is an excellent. Yes.
It's also the means by which people even started studying quantum physics. Like what you just looked at and walked through was how we discovered that the quantum world behaves differently than the world we see and interact with.
Is it not included in the world we see?
It is. It is. But how we, science is often, and physics, at least in my experience, is often about explaining why things work. And sometimes that goes into what they have discovered basically is what we see and larger, like the size of things matters when understanding how they work. With the models we currently use, because all we could really explore was what we could touch before, but now we have tools that allow us to explore things really, really small and then things way bigger than us, right? And so that's how we learn that about relativity, right? Because things that are much bigger than us also behave differently in relation to us on Earth. And then when you go to the quantum level, when we're talking about quantum, what we just mean is very, very small, right? Like much, 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 much smaller than us. That's all it means. And so when you're doing quantum physics, you're just investigating the world at an electron size. And we have discovered through this experience that when you look at things in an electron size, they're doing stuff, something different is happening than what we were assuming was happening at the human size, if that makes sense.
Totally.
And are we made up of a bunch of atoms?
Yes. Yes.
As far as we know.
As far as we know. There's still a lot of unanswered questions about all of this, but well, you just learned a big piece of what quantum physicists know. And just as Raquel, it was so exciting watching you reason through that, because it's literally the reason why quantum is exciting. It's like, what the heck is going on here? Like, oh, we didn't know we should explore things at this size and that it's going to tell us something a little different.
So I have a PhDs are supposed to be philosophical, whether we are or not is a whole nother thing.
Right.
But so, because, like taking it out of the physics, like I know I'm taking this question out of the world of the physics, which is the small atom and the question of acting as a particle and as a wave. But it makes me think of the ways we relate to ourselves as individuals rather than as individuals that are part of a wave of what's ever happening. And so that relationship of what's happening individually in my life as if I'm separate from this other overall interacting patterns. So there's something about the ways we see the world, the way we see each other, and understanding that we are both a part of things, even as we're individual, that's exciting to me in the quantum, and I think for many, because it gives expression to the individual and collective at the same time. I know I don't have there's a question, maybe that's a wondering. I have a wondering in this that doesn't have a form to it yet.
I like that philosophical takeaway. Mine was more like, every time I watch that black video with the screen, it makes me think of processes by which things are built. It's a reminder that time is like not real, right? It's not, well, I shouldn't say it's not real. It's not linear.
Right.
And so watching that non-linear process that happens over time, right, is so interesting. And it makes me think about how in order to build things, we often start building linearly, but really nature doesn't do that. Nothing in nature does that, right? Like everything kind of does that. and then it becomes a thing. And I think that's really beautiful.
One of the things your experiments looked like to me was connection and how things are connected and movement. And when Raquel, you said things are more connected than disconnected, that seemed to really fit us as humans, not feeling separate from each other somehow, from a scientific standpoint, how we all came to be, which I have no idea. But I felt more positive that we actually have science to back our connections, our connection activity, our need to be a part of something and keep building with what we have. Because like those particles just kept going. They didn't like stop and say, well, I don't know. You don't look like me. I don't think I'm going over there. They just kept moving.
Yeah, like at that given slice of time, they did not have a relationship with one another. And it's an interesting dance, I think. And I know, Carolyn, because we've talked a little bit about this, but there's that thing of like, what do we need science for as we're human beings building our relationships with one another? And then where does it fall apart? Because as you know, Simone was saying, this is the science that happens at a very small level that is not the same description of what we see at a larger scale. And then we're in a different arena. So it's kind of like there's similarities, but there's I don't know. I think for me, it's always this like, why do I need science to back up that there's a benefit to being kind to one another? Why do like what's science in that for? We are connected to one another. It does feel really cool to be like, oh, and atoms are too. You know what I mean? Like, but
Well, I think
yeah.
that kind of is where the science and art and society all interweave, right? Because the ideas that we come up with in science are generated by humans. And so it's like, yeah, so the science ideas affect our culture, and our culture affects our science ideas and our art. And so it's all kind of interconnected.
But you need science to build bridges and fly airplanes. All of those emerged in the context of science evolving. And unfortunately, it's the same science that creates bombs, but that's sort of been so science is a tool for humans, and it's also depends on which humans have control of it, I guess.
Or what we do with it. And I'm hearing a friend of mine saying engineering is like the second cousin or the stepchild of science. Because the engineering, so both the science of where we discover things and ask questions, and engineers who are building and constructing. And I was thinking when bridges have been built and what we know and how we know. And there was a statement in here earlier by somebody who had to leave because I believe we were coming up on our close, which was, and more? More? Can we have more? Because I do feel like this is just the beginning, and I really appreciate. So I'd like to do a closing, and if Carolyn, Nick, you're open to that, I
Yes,
do
I do want to. And Simone, did you want to introduce yourself
Yes,
at all?
please.
So what we did is we just talked about how we got excited about quantum and physics and stuff. Very briefly.
We're learning who Simone is and then closing. Yep.
Oh, hello, I am Simone. Here we go with the introduction. I told you, Carolyn, I don't do this well. My
You'll
name
be
is
great.
Simone. What is the question? I didn't hear you. I'm so
How you you know, so we were kind of all sharing well, I guess physically, geographically where you are, and then you know, like what got you excited about joining us for this adventure and or physics and or quantum.
I am physically right now in the DC area. I live in Philadelphia. I trying to think of what my background is in physics. So I've studied physics and got excited about physics very young. When I was in high school. I don't think I've ever been that excited about quantum, but I am very excited about how physics shows up in our daily lives and how we all are physicists every day. I'll maybe say that.
Thank you. And it felt it. You were so helpful when you came in and the grounding it was amazing. It was like this experience of having come through the session and then going poof, exclamation point. So it was like awesome. And this is really beautiful. So this is one of a number of science related invitations to explore together, that individuals can have the freedom to gather to explore and question ideas around what's in the world and with each other and what freedom looks like and independence. And where the Freedom Festival is an independent activity, it is an organizing activity of people inviting each other into things that they care about, so they can do that with people that they've just met or people they've known for years. There is into the chat, we might copy paste some of the links from the very top, which includes an invitation to donate, because we offer these sessions for free, and yet organizing and bringing these pieces together, of course, takes some funds. So whatever you give, we put directly into building the Freedom Festival. We have a conversation with another physicist, an astrophysicist, Hakeem Oluseyi, who is the CEO of the Astronomical Society of the Pacific. And also, you might have seen him on the Science Channel. Importantly, he is a human being who grew up in rural Mississippi and went up through Stanford and continues to bring the grassroots to studying the stars and is interested in conversation with us. That's July 2nd. Check out all the other sessions happening online through July 4th. The closing is a poetry reading open mic and also a conversation with Frederick Douglass around what is the 4th of July to us. Thank you for participating, because we are humans in the world and together we can make it more and more beautiful. So thanks for being here.
Yes, and I threw in the chat an invitation to join Simone, Nick, and I for a quantum learning ensemble this fall, which we are still figuring out what it might build to be, but we welcome your curiosity and what you would like and what you would enjoy.
Wonderful. See it in the chat and see you soon.
Are we dancing or no?
Oh,
My molecules are dancing. I can't see them, but I know they are.
My atoms are dancing.
They are. Yes, they are.
It's called the atom dance.
Don't you know?
oh no, it stopped. Why did it stop?
Oh no.
I don't know. It'll come. Thanks for being here, y'all.
Talking about
Yeah, thank you so much for coming. Thank you for staying through to the end.
Thanks, Ann.
Don't you know?
Maya, it's a pleasure to meet you. Carla, Albert.